Okay. Now recording now. Okay, let's
Yes, miss.
go back to where we were, like what we were doing. So you said there is friction, and you said it is to the left. My question was, by any chance, do you know how much the friction is? So this is the friction, right? Friction. I'll put simple F for friction. Hatfi is asking, is it 5 newtons? What do others think?
It's greater than 5 newtons.
Okay, so Bimandi also said earlier, it's not moving because she said there is friction, but it is not moving because the friction is greater than the 5 newtons. Um, what do others have to say about that? That friction is greater than 5. And about what Hatfi is saying, Hatfi thinks it is 5. Can others join into this discussion? Bimandi
It
says
would be.
is it
It
can
would be.
now Bimandi says it can be equal to 5. Mihir says not greater than 5, only 5. Malit, you're saying it could be. Sasindu is also thinking it's 5. Malit, you're saying it's same. Now Mihir says
Miss, could you repeat the question? I disconnected.
my question is on this object,
Uh-huh.
are you able to say the size of friction acting? How much is the friction? Are you able to say how much?
Yeah, can say the amount of friction acting. Is it in equilibrium, Miss?
I have given you that it is not moving.
Ah, yeah. Okay. I understand. Sorry. Yes, we can tell the amount of friction acting.
How much?
5 newtons.
5 newtons. Uh, is it exactly 5 or more than 5? Now, because earlier some of you said
Exactly 5.
it's
Exactly
exactly
5.
5.
Yeah.
Tell me why it can't be more than 5. Now, Mihil said that he said not greater than 5, only 5. I like that answer. Why it
Miss, if
can't be
it's like greater than 5, it will move to the right. I mean left.
nice, Mihil. If it is greater than 5, there would be a resultant force acting. It's not balanced. It will start moving to the left. Very good, Mihil. So it is exactly 5. You are certainly able to say the size of friction. If it is not moving, uh, so the forces are balanced. So it must be 5. But now I have a question for you. Now, how did you know there is friction acting? It's not moving now. Even when here it was not moving.
Miss, you didn't mention there is friction. You said earlier you don't need to mention something like that.
No, here the object was not moving. uh, no. Uh, here the object was not moving. That's why you said there is no friction. So why the same argument doesn't work here? It's not moving, so there must be no friction. So this, do you see that this? So is this reason correct here? Is that why you are able to say? Because I should say here also it's not moving, so there is no friction. Yeah, we are pushing it here we are pushing it, but it is not moving. Here we were not doing anything, so it's not moving. So it's not moving, no friction. Here, true, I'm applying a force on it, and it's not moving. So if it is not moving, there should not be any friction. Can you argue with me? So why is there friction here now? Due to what reason? Here it was because it's not moving. That's what you told me. This is the reason you gave me, not moving. In the second case, what is the reason you would give me? No friction. Why? Because no motion. Now you can't give me the same reason here. Because now you're saying there is friction, there is friction.
Because according to Newton's first law, since the two, we came to a conclusion that F is equal 5, right? 5 newtons. so by applying Newton's first law, which states that when if an object is in equilibrium, it has to be either at rest or moving at a constant speed. So since this is at rest, since at both sides the forces are 5 newtons.
No, no, no. You gave me that. Now, what I had given you was that it was not moving. You were the one came up with this. I'm asking how you knew there should be F here and that it should be 5.
Because forces act in pairs. If you have like there always has to be a reaction force.
Yeah, there are no action-reaction pairs here. There are no action-reaction pairs here. Action-reaction pairs don't act on the same object. All these 4 forces are acting on this object. The reaction to this one is somewhere else. The reaction to that is somewhere else. The reaction to it is somewhere else. The reaction to F is somewhere else. Neither of these are action-reaction pairs. Abhimanti says because a force is applied to move the object. Okay, I can take that.
Force involves 2 parties.
Again, yes. So we are looking at one party here. We are looking at one object and all the forces acting on that object. So each of these forces are exerted by different 4 forces. 4 different things are exerting them. I am pulling it here. This reaction is this is pushed by the surface. This is pulled by the earth. This is pushed by the ground, the surface again. Push or pull, whatever that is. You knew that there has to be a friction because it is Newton's first law, because it's not moving. If you know if it is not moving, the forces has to be balanced. Then when you consider vertical equilibrium, fine. R is there to balance W, W is there to balance R. When you consider horizontal equilibrium, there has to be something to balance the 5 if it is not moving. And what could it be? That's the friction. But then there is kind of a what do you call it? I forgot the word. I will say it if I remember it. It's something opposite to what you said here. You said if there is no motion, there is no friction. Contradiction. Thank you, Hatvi. I feel like there is a contradiction in what you are saying here. Since there is no motion, you said no friction. Then but now you are using the same reason to argue the opposite. You are saying, yeah, because it's not moving, there is friction. Here, because it is not moving, there was no friction. Now, because it is not moving,
but there was a force applied in the second.
There was a force applied in the second. Yeah. So basically, just because an object is not, no, you're correct. Just because an object is not moving, you can't say there is no friction. That's what I want to put across to you, the message that I want to put across to you. Because people tend to think if an object is not moving, there is no friction. Friction is there only when things are moving. Didn't you think like that at some point in your life? Friction acts only when something is moving. Did you not have that idea in your minds at some, I don't know whether still you have it?
Yeah, I did.
Yeah, right?
I used to.
Yeah. We think that friction acts only if something is moving. So the way we need to correct that perception that we have is like this. Friction will act, definitely it will act if something is moving, and also if something is trying to move. This is trying to, now here it was not trying to move, no one is trying to move it. Here somebody is trying to move it, so it is trying to move. Friction keeps it from moving. So friction acts in 2 cases. If something is moving, friction acts, true. But there can be friction acting when it is not moving too. If it is just trying to move, it's not moving yet, but it's trying to move. Somebody is trying to move it. Okay. Then there is friction acting. The moment when you try to move something, friction starts to act to oppose your effort, of moving that object. Okay. So, okay, now same object. One more scenario. We might be taking a little too long for this, but I think this discussion is important. Same object, same surface. So you have the weight and reaction acting on it. And I increase this force to 7 newtons, and it is not moving still not moving. What can you say about friction? Is there friction? If there is friction, in what direction is it? If there is friction, what's the size of it? Are you thinking, or am I stuck again? So when you are silent,
Thinking.
You're thinking. Great. Please think. I like when you're thinking. It's just that I can't see that you're thinking. I think that I'm stuck. Let me write here. You said this is 5. In this new scenario, I have increased my force to 7 newtons. It's still not moving. I still can't move it. It's not moving. Bimandi says there is friction towards left with magnitude of 7 newtons. There is friction, and now it is equal to 7, she's saying. Okay. Opposite direction, 7 newtons. Sasidu agrees. So this force friction, it can change in size. Malit agrees. Okay. It can change in size. It depends on how much you are pulling the object with. So if I keep increasing my force, at some point it will start to move, right? Suppose, so there is, we call it the critical point. So you're pushing something, you're pushing an object or pulling an object, whatever. So if you start your force with a small size, 1 newton, not moving, 2 newtons, not moving. Give me a moment, what happened? All right, okay. 3 newtons not moving, 4 newtons not moving, 5 newtons not moving, 6 no, 7 no. So say you pass 7. 8, suppose at 8, it starts to move. Right at 8, it barely, okay, right at 8, it's about to move. Let me say that. It's about to move, okay? Now my next scenario, same object. Sorry about my very ugly diagrams. 8 newtons. I will say, I won't say not moving. I will say about to move. It's about to move, but not moving yet. But the next thing, it start to move. We call this limiting equilibrium. We call right this moment limiting equilibrium, because all this time it was in equilibrium, proper equilibrium, nice equilibrium. Now limiting equilibrium, it's about to lose its equilibrium, limiting equilibrium. If I change this to 8 point, like it's the limit, If I increase this further, this will start to move. If I increase this by the slightest amount, it will start to move. This is the last point that this can hold on without moving. How much is the friction? How much is the friction? It's not moving. It's just about to move. Then, and it is called, it's still equilibrium, limiting equilibrium. So it's 8 newtons. Friction is there and it is 8. And now I said, if I further increase my force, say I make it to 9. Let me draw it here. If I make it to 9 now, if I make it 9, you have W, you have R. I increase this to 9. Then this will start to move. This is what I call this limiting equilibrium. This is limiting equilibrium. Equilibrium. Here, it moves that way. It accelerates. It starts to accelerate that way. Is there friction? In what direction if there is friction, and what's the size?
The friction force is less than 9 newtons.
Less than 9 Newton. It is there, right? There is friction acting in
Yeah, there
the
is
same
friction.
direction. There is friction, and this will be equal to, now this was the limiting. Now limiting means that's the maximum up to which friction can increase for these given two objects, for this object and this given surface. The maximum friction that can act between these two objects is 8. That's why that was the limiting. If you pass that point, if you increase your applied force greater than that amount, friction can't increase anymore. It will stay at 8. There will be that maximum friction will continue to act on this object. So it will be 8. Now, to whatever amount you increase this, 10, 20, whatever, friction will stay at 8. It has increased to the maximum that it can. This is called the maximum friction, F max. We call it F max. So here also at the limiting equilibrium, that is F max. That's why we say it's the limiting. So if your force is equal to the maximum friction, that is limiting equilibrium. And the moment you pass that size, it will start to move. And then F max will stay at that value, F max, 8 in this case. Is this clear? Hello? Anybody there? Ah, okay, yes. Okay, right. And this maximum friction, okay, that can act between two surfaces can be calculated. It depends on only two things. The maximum friction that can act on an object depends on two things. One, the reaction. You would never imagine. Maybe you might imagine that it depends on R. It depends on R. How far this can go, how far this can increase, that maximum friction depends on the reaction force, R. And it depends on the roughness of the surfaces. So there is a certain quality for this about the surface, which is called the coefficient of friction. It's a measure of the roughness of the surface. So it depends on what is called the coefficient of friction and the reaction force acting on the object. Okay, so this F max, I will give you the note in a little bit. F max is the product of R and mu. So it's mu R. What is mu? I didn't say what mu is. Mu is coefficient of friction. Coefficient of friction. Okay, it is a constant to a given two pairs of surfaces. It's a constant. So that times the reaction of the object, the normal reaction. So for example, if somebody pushes this down, this object, if you say you keep something, a heavy object on top of this, that would increase what? That would increase the reaction. How is that? That would increase the total weight. That would increase this. So there would be an additional, it's like now it's like one combined big object, right? So the weight will be, it's not the sole weight of the object, it's plus that. So weight of the combined thing will increase, then R will increase. When R increases, it's harder to push. That's why if you have something stacked upon something, it's hard to push because the friction increases too along with that. So friction depends on mu and r, and that's the maximum friction. Maximum friction depends on mu and r, and it can be calculated using this formula. Let's write that. We talked a lot. I'm tired talking. Let's quickly write in point form. Under friction. Right under friction. First bullet point in bullet points, point form. This is happening again, no? This getting stuck thing.
Miss, what connection do you have?
SLT.
SLT 4G.
Yeah. And fiber.
Oh.
I
Miss,
don't know why. And
do you think
I'm using my brother's laptop.
Miss, you're using it wire like through the cable or wireless?
Wi-Fi.
No, no. I
Wireless.
mean like, huh?
Wireless.
Wireless.
Miss, do you think the internet is over?
I don't know whether maybe my what do you call it, the data is over. About like it's the end of the month, no? 20. What's the date today?
26.
26th. I should check that.
Miss, you should put a package. There's a package in SLT for like online education. People who are like having their online education,
Yeah.
they give extra 30 GB for Zoom and another app called Microsoft Teams.
Teams. Yeah.
Yeah,
Really.
yeah, you should get that. They have like they give 30 GBs for 300 something rupees. Maybe if you're interested.
195.
300 something. Last I checked.
Ah. I should check that out then. I will do that. Thank you, Malik, for the information. Now, is it recording? It is, right?
Yes, miss.
Yeah, okay. Okay, let's write. First bullet point. First bullet point. Friction is the tangential force. Friction is the tangential force
Miss, what? Tangent?
tangential. Tangential. Look at
Tangent.
tangential. Like the reaction is normal, perpendicular. Friction is tangential, goes along the surface like a tangent. Friction is the tangential force that acts opposite to the motion, opposite to the motion or intended motion. Your object need not move. If it is intending to move, friction might act. Friction is a tangential force that acts opposite to the motion or intended motion of an object. On a rough surface, of an object on a rough surface. Second bullet point. Second bullet point. Friction counteracts any applied force. Friction counteracts any applied force. Friction counteracts any applied force trying to move an object. Friction counteracts any applied force trying to move an object up to a maximum. Up to a maximum. After which the object begins to move. Yes, Malik.
Excuse me, miss.
Yes, Malik.
Applied force trying to move an object.
Friction counteracts any applied force trying to move an object up to a maximum. After which the object begins to move. After which, the object begins to move. Third bullet point. Third bullet point, for any two surfaces, this maximum friction F max, write F max in red, simple F, subscript max, F max. For any two surfaces, this maximum friction F max
Miss, you call it limiting friction.
limiting
Right?
friction, yes. For any two surfaces, this maximum friction F max is called limiting friction in red, limiting friction for any two surfaces, this maximum friction F max is called limiting friction, and it depends on the reaction force between the surfaces, capital R, R in red. It depends on the reaction force between the surfaces, capital R, R in red. And the coefficient of friction in red, coefficient of friction mu of the surface, mu. This is mu in red. Depends on the reaction force between the surfaces R and the coefficient of friction. So it's a constant, right? Coefficient of friction is a constant for a given two surfaces, and the coefficient of friction mu of the surface. Next bullet point. You write the formula. Oops. You write the formula. F max is equal to mu times R. Next bullet point. It's blur. Next bullet point. You draw, like just to show an applied force. If there is an applied force, then there will be friction. Okay, and under that, right, as long as there is no motion, you can be applying a force, but it might not be moving. So as long as there is, we'll say as long as the object is not moving, the object is not moving, F is equal to applied force. You know this. This is what you said. And F is less than F max, correct, right? F is less than F max. As long as object is not moving, your friction exactly balances the applied force. It's equal to the applied force, and it is a value less than the maximum friction. As long as object is not moving. Next bullet point. We say about to move. About to move. If it is about to move, that means this is your maximum friction acting now. Oops, sorry. You can write when the object is about to move. Within brackets, we call it limiting equilibrium. Limiting equilibrium. F max. When the object is about to move, F max has reached or has been reached. F max has been reached. And still F max is equal to applied force because it's still in equilibrium. The two are still balanced. But now your friction is the maximum friction because if it's the limiting. So it is limiting because this is the maximum. Okay. And finally, if under your applied force, if this is moving under your applied force, if it starts to move, once motion starts, friction remains at F max. And that means applied force is greater or F max is smaller. This is greater than your F max. You have exceeded the maximum friction that can occur between the two surfaces. Now, if you understood our discussion, that is enough. I gave you the note for that. The note can be, I don't know, sometimes, okay, I'm sorry, I'm just seeing that you have dropped messages on the chat. Oh, you can't hear properly. Okay. Where do you want me to repeat from? What did you miss? Everything is on the screen. You can see this, what? Sorry. Sorry, Sasindu. What did you miss, Sasindu? Now it's, no, it's okay. Can't hear. You can't hear me. Can others hear me? Is my voice dropping? Now, okay, okay,
No.
okay. Okay. Uh, Now let's look at, okay, Nathan, now let's look at a couple of questions where friction is involved. Now for you, uh, there is one more thing that comes under friction. I will do that next week. That it will be too much for you to bear. Uh, from what we did so far, we will do a couple of questions, and the other thing I want to tell you is in questions, this applied force happens to be in lot of the questions. Instead of giving you a scenario where an object is kept on a horizontal surface and you pull it or push it to a side trying to move it, instead of this scenario, what they give you is an object kept on a slope, because then there is a natural force that is trying to move it without you externally trying to pull it up the slope, or did I use the right word? Push it up the slope or pull it down the slope. Just when you keep something on a slope, it is trying to move without any really external forces. What is that force that naturally is there trying to move it down?
Wait.
Not the whole weight, a component of the weight. Weight acts this way. But then there is a component. You can think of, you can break your weight into two components perpendicular to that slope and parallel to that slope. So this part of the weight is completely trying to move it down, pull it, pull, no, pull it down the slope. You don't have to apply any forces. There is a component of the weight trying to pull it down the, move it down the slope. So if this is not rough, this will slide down. If it is rough, there would be friction acting, and depending on whether the size of the friction is enough or not to counterbalance the component of the weight, that will decide whether this will move or not.
Excuse me, miss.
Yes.
Can you show the last point again?
Last point again. Yes. Before I turn the page, Hatfi is asking, so the net force is the blue line? No, this is the weight. This is just the weight. Net force, there are other forces. There is the reaction, like that, acting perpendicular to the surface. Then there will be friction. So it's not the net force. Okay. Okay. So for Malit, here's the last bit. Would that be enough, Malit? This is what you want?
Yeah, miss. Give
Okay.
me 10 seconds.
Yes. 1, 2, 3, 4, 5, 6.
Okay, miss.
Ah, nice. So it was literally Latin. Because when people say, give me a second, they never can get back to you. They just say, give me a sec, but they never. Okay, anyway. Let's look at a question. Let's look at a question from the book. Oh, wait, okay. Yes, let's look at mm, 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 yeah. Let's look at you do you all have your textbooks with you? Do you have your textbooks? No? You don't, or do you? This is page 106 in the book. The question that we are going to do now. Shall I? Okay, so you have some form of the book, the PDF, soft copy, or the hard copy, the original book, borrowed book, a stolen book, something. This is the question. Number 15. I'll keep it like that. This is page 106 in your book, number 15. We are going to try this question. Okay? We will do it together. So, as I said, the only formula that you have to apply in these questions is F equals ma. That is it, right? And then if you have to find, if there is friction involved, you might have to compute F max using mu r. And then once that is computed, that is just a force now. And then there are a couple of forces acting. You will have to apply F equals ma. But, and you apply it in the direction of motion. So let's see, okay? Can you draw a diagram for this question? A particle moves up a line of the greatest slope of a rough plane. What do you mean by that? Here's a rough surface, rough. If I keep it as a slope, something is moving along its greatest slope means it's moving like that, not going like this at an angle, not going at an angle. If this is the slope, it's going down the slope like that. That's the meaning of greatest slope. Okay, so it's coming directly down, not like going sideways. Okay, so don't, that's just there to make sure it's going down like that. So a particle moves up, this is moving up a line of greatest slope of a rough plane, rough meaning there is friction, plane inclined at an angle alpha to the horizontal, where sine alpha is 0.28. The coefficient of friction between the particle and the plane is 1/3. Show that the acceleration of the particle, so you have to find A. This is about F equals ma. Show that the acceleration of the particle is -6 meters per second squared. If you need to copy the question, please quickly do. And can you draw up a diagram, sketch a diagram for this? Can I move the book? Can I remove the book? Move, remove, anything. Can I remove the book? Where's Rachel? Rachel is not here. Netni is not doing. Rachel and Madara. Anyway. Now, another thing to notice here is that now you know that this is about applying F equals ma. So sounds like we need to know the mass of the object, mass of the particle, but it's not given. It's not, if the mass is not given, it's because you don't need it. Okay. But to apply F equals ma, m is there, so you need something to put there. So let's take it to be m. If the mass is not given, you suppose that it is m, and you will see it gets cancelled off. So that's why they don't give it. Okay, you don't need the value of m. So in this question, mass of the particle is not given. You let it be m. You have to mention somewhere, let the mass of the particle be m. So I hope you tried a sketch. I will show you how to do the sketch. This is the first example you are doing under forces forces and motion. Here's how you should draw your diagram. Okay, see whether you have gotten something close to what I'm drawing. So this is number 15. On page 106. You have a slope. Angle is alpha. Sine alpha given, you note it down on the side. Sine alpha is 0.28. You have your particle on this. It's moving up the slope. If it is moving, it's moving with an acceleration. You put a double arrow and mark the acceleration as A. That's what we have to find. Then you draw or mark all the forces acting on this particle. So this is why we practiced drawing free body force diagrams. This is why we practiced how to think what are the forces acting on an object. This is on a rough surface. The first force that you will anyway mark is the weight, and draw long arrows. Weight, W. Mg, W is mg. So we have taken, let the mass be m. Mass of what? Mass of the particle. What else? Mg. Then the reaction acting perpendicularly up, normal reaction to the slope, R. What else? What else? What other forces are acting? Quick. Friction, good. F. What direction? Up the slope, down the slope, up or down. It's tangential, you know, it's along the slope. Is it up or down? It's down. Because it's moving up, your friction would be acting down. Is it the maximum friction? Can I mark it F max? If so, why? Is it just some F or F max? Is it a friction lower than the maximum friction, or is it the maximum friction that could act between these two objects? Yes, because it has started to move. So it is the maximum friction acting. So you mark it as F max. So this object is acted upon by three forces. There are three forces acting on it. Okay, and it's moving that way. Okay, now before you can apply F equals ma in that direction. Remember I told you, you apply F equals ma in the direction of motion, but there is a direction along which it is in equilibrium. In a certain direction, it is in equilibrium. What is that direction? This way. Perpendicular to the slope forces have to be balanced. How do we know? Because it's not flying up, nor is it going through the surface into it. Vertically, the forces are balanced. It's only moving. Now, when I say vertically, my word vertically is with respect to the slope. This is my new vertical. This is my new horizontal. Okay, with respect to the slope. See, I'm tilting my head and looking at it. I'm tilting my head because everything happens with respect to the slope, in relation to the slope. So vertically, the forces are in equilibrium. It's in vertical equilibrium. But horizontally, it's moving. This way it's moving. That way, this way equilibrium, this way moving, acceleration. Okay. So let us first apply vertical equilibrium. Vertical equilibrium. Let me start writing here. If you consider vertical equilibrium, vertically it's in equilibrium. What can you say? R is equal to let's split mg into the two components. You always have to, now you know this from the previous this thing. Let's replace mg. I'm replacing mg. I'm throwing mg away and replacing it with its two components. What is this? I hope you can use a little bit of geometry, or you can remember it. If this is alpha, this angle over here would be alpha. Okay, the angle between this vertical line and the weight line is alpha. So this is mg what? Cos alpha. This is mg sine alpha. Is that clear? Are you with me so far? Are you with me so far?
Yes.
Right? So now I don't have to worry about this mg. I have replaced it with the two components. So I have all my forces acting in the two directions. You know that anytime when we have slant forces, we break them down into components. That's what I did. So in this way, my forces are balanced. Vertically, my forces are balanced. So R is equal to, sorry, there is a lagging, mg cos alpha. R is equal to mg cos alpha. It's important to find R here by using vertical equilibrium, because to find F max, to find the size of F max, we need R. And the way to find R is by taking vertical equilibrium. Okay. Now, since we have found R in terms of alpha is something they had given, M, we would wish that it would cancel later, G is just 10. So we have found R. Let's write what F max is. We can compute F max. F max is mu R. Mu is given as 1/3. So it's 1/3 mg cos alpha. I found my F max. I'm just finding all my forces and keeping, because when I apply F equals ma, I would need all these forces. Okay. Now a quick review. I splitted my weight into two components. I found R, I found F max. So all forces are like found in terms of alpha and M. Now I can apply F equals ma in the direction of motion. So you have to show with an arrow. Here I'm going to apply F equals ma. It will appear in a little while on your screen. I'm applying F equals MA in a direction up the slope. I'm very sorry, okay? And my IV, yes, I'm sorry. My IV cam is also not working. Ayyo. Okay, it came. Let me start recording. So this is going to be like how many? No, the recording is still going, right? Recording is still going. I'm not sure where you lost me. So I was saying we have found there were originally three forces acting on this object: the weight, the reaction, and the friction. So the weight we split it into two components. So it is expressed in terms of alpha, what they have given. And then R I found here and F max I found here. So they are all found now. So I'm ready to apply F equals MA. So you apply it up the slope. So you have to, showing this arrow is very, very important. Without this arrow, nothing will make sense. You have to say in what direction you apply F equals MA. You apply it in the direction of the motion, F equals MA, that way. Okay. Now, what? Okay, so you're applying it in that direction. Okay, so any force in that direction is positive, any force in the other direction is negative. Okay. So what is my resultant in this direction? I only need the net force in that direction, in this direction. I don't have anything acting up. I have two forces acting down, the component of the weight and F max, and they both have to be written as negative. So minus mg sine alpha minus F max. Let me write F max first. I have found it here. I can put this in the next step. That's all right. Those are the only two forces that way, and they are negative. Is equal to M is the mass, A is A. That's what I want to find. I want to find A. Now let me put what is F max. So that is minus mg sine alpha, minus mg sine alpha, minus F max is 1/3 mg cos alpha is equal to MA. Do you see? All terms have M in common. I can divide the whole equation by M and I can cancel off the M. I don't need it. Now, the rest is up to you. Sine alpha is given. Using that sine alpha, you can find cos alpha and you compute what A is. Simplification is up to you. You have to get A equals, the answer is -6. Can you see whether you get this? How do you find cos alpha when you know sine alpha? You need cos alpha na? How do you find that? Let me do that in a little bubble here. You can use this sine squared alpha plus cos squared alpha is 1. Sine squared alpha would be 0.28 squared plus cos squared alpha is 1. then cos squared alpha is something, then cos alpha is the square root of that whatever thing. Again, no, I'm not. I'm not muted. Others, can you all hear me? Malit says I'm muted. I'm not muted.
Miss, the message was given 7:28.
Sorry, I'm just...
Hello, miss. I came back. I just lost my connection.
Okay. Can you see whether you get this answer? What do you get for cos alpha? Does someone have cos alpha? How much is cos alpha? Come on.
Miss, cos alpha is 0.96.
Very good, 0.96. That's right, 0.96. So you put it there and make A the subject, solve for A, and see whether you get -6. You get it? And for G, you put 10. G is 10. So 10 times sine alpha is 2.8 minus 2.8 minus 1/3 times 9.6 equals A. That's what A is. Is that -6? Minus 2.8 minus 2.8 minus 3.2 is A.
Yes, miss.
-6. Yes, Bimandi. Yes, Malit. Okay. That question has another part. I would like you to try it. It's from just equations of motion. It's the second part of this question. You have the question. You do it. Then number 16. No, don't do it. Don't do it. We will do it together. Okay. Because before you do that, we have to do some more questions like this to practice. Okay. There is some additional thing that I told you earlier about friction that we have to learn, but that will be too much if we do it today. So we will continue from that.